Hello guys, so welcome to our last video on lecture 8, in which we're gonna also cover very important point about Karnoff maps. Okay, we're gonna use Karnoff maps in the rest of our course, and this special point or topic that I want to discuss now, we're gonna encounter a lot in our course, in which we're gonna deal with what's called don't cares. So basically, what is the definition of a don't care? Okay. Okay. So if you have a function that is a function of two Boolean variables, then you have four possible combinations for the input: 0, 0, 0, 1, 1, 0, 1, 1. But what if your application, I mean the input of your application X and Y, can be 0, 0, 0, 1, 1, 0, but for some reason, based on your application, it will never be 1, 1. Okay. So basically, in that case, you don't care about the value of the function at 1, 1, because this will never happen, right? So that's basically why we call it don't care, because for some particular combinations of the inputs, okay, we don't care about the value of the functions. And this is one of the examples that I just mentioned, that your application, for example, this specific input will never happen. So basically, whatever X and Y, this will never affect your the performance for application. Okay, if you assume that at X equal to 1 and Y equal to 1, or F equal to 1, or if you assume at X equal to 1 and Y equal to 1, F equal to 0. So we don't care, 0 or 1, this will not affect my application. Okay, to be more clear again, we take some example. Okay, because these don't cares can affect our minimization a lot. I mean, affect it positively if we consider them, as we will see now in this example. So here we have a function of four variables, w, x, y, z. It's a sum of five minimum terms here: 1, 3, 7, 11, and 15. And you have don't cares at 0, 2, 5. I mean, at minimum term 0 or minimum term 2 or 5, you don't care about the value of the function, whether 0 or 1. So let's locate, before we go to the Karnoff map, let's imagine it practically on the truth table. So here is f will be, so this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Four variables, 16 combinations. It will be 1 at 1, and at 3, at 7, at 11, at 15. Don't care at 0, 2, 5. Don't care is usually the symbol for don't care is X capital. Okay, so don't confuse it with variable X. So at 0 you have a don't care. At 2 you have a don't care. At 5 you have a don't care. How about the rest? The rest is zeros. All other combination, F will be 0. Okay, so let's now understand more, what's gonna happen at 0, 2, and 5. Basically, one of the practical examples is that these three combinations will never happen. I mean, in your application, W and X and Y and Z will not take zeros at the same time, which is minimum term 0. Okay, same for 2, same for 5. Okay, so let's now locate such F on our Karnoff map. So I get here, the Karnoff map from the book, okay, with the solutions there. So we're gonna just fill ones at the minimum term is 0, 1, 3, 7, 11, 5. So this guy is 1, 3, 7, and 11 and 15. Okay, 1, 3, 7, 11, 15. Okay, and we have don't cares at 0 to 5. Don't care at 0, don't care at 2, don't care at 5. Okay, let's now simplify this. Okay, let's start by the isolated one, the one with, less number of neighboring ones, which is that guy here. Okay, in our regular way to solve this, we usually take this with that guy. But since you don't care about the value of the function at minimum term 0 and the minimum term 2, okay, I mean, you don't care. It might, if it was 0, if the function was 0, if the function is 1, this will not affect your performance. So if we assume that there is 1 here, so let's do it with another color. If we assume there is 1 here and 1 here, okay, then if we take these 4 together, this will make our final form of the function is more simplified. Let's do both. Let's do both. Let's do that guy and let's do, the bigger one. So let's change the color. So let's make this smaller guy is green. Okay. So for the smaller guy, smaller group, we have this is basically W X bar, W bar X bar. And Z, because W is not changing, X is not changing, and Z also is not changing. Okay, then plus, then we have these 3 ones. So let's make them with another color, for example, blue. So you have here X is changing and W is changing as well. You have YZ. There's 1 here. So YZ. If we implement this, you will have an AND gate with W X bar Z as input, another AND gate with W and Z, then an OR gate. Okay. Now let's do it with the red group. I mean the group in which we put 1 and 1 at the locations of the don't cares, here and here. Now we have a bigger group for that isolated one, this guy here. So if in that case equal to this group here will be W, it's 0, 0, will be W bar X bar. Plus this group again has no change, which is WZ. Now let's see the implementation of this. W bar X bar YZ, then OR gate. Which is more optimal? Of course, this. That's more optimized in hardware, because this gate here and this gate here are different circuits. They are AND gate. But the second one here has only 2 inputs. So the circuit itself, the transistors and stuff will be simpler. You may have less number of transistors. So less power consumption, less area. So it's cheaper in implementation than the first one. So we will not adopt, since we have a don't care and we are smart enough to and we know that the application don't care about the value at these combine at minimum term 0 and minimum term 2. Okay. I mean by don't care, if for any reason, noise, for example, some glitches happens in your system, and you have W equal to 0, X equal to 0, Y equal to 0, Z equal to 0, okay, at that particular location, At that time, f will be equal to 1 because we converted this don't care into 1. But this will not affect the system. Okay, the function of the system will not be affected. Of course, this may be not clear, still not clear for you because you can't see some such applications. But we will see such applications in the future in that course. For example, what's called the BCD counter. This BCD counter is a 4-bit counter, okay, that counts from, remember, if you have 4-bit, then this number is 0, and the last number is 15. This is 0, this is 15. But the BCD counter is a decimal counter. So it counts only from 0 to 9. And you don't care about this. So there are many practical applications that have don't cares. Okay? So if this is, for example, in an exam or something, or even in your practical life, in a company or something, what you're gonna do? You're gonna do this. Don't do that. That's not optimized. Maybe someone of you may think in another way. Okay, let's again start. So this is solution 1, which is that one here. But there is another solution which is also optimized, solution 2. What it is? Again, we're gonna look at that lonely guy, with less number of ones connected to it or adjacent to it. In the first one, we take this group here, but based on the same principles that we can change x into ones or zeros based on our choice. How about this guy here? Let's change this x, this don't care that was here, into 1. Then we can take this as a group. So f at that time will be equal to, so basically it's equal to, so here is z, and you have w bar z or w bar z, just to make it in order. Okay, so basically y is changing, 0 and 1, z is not 1 and 1, and here 0 and 0, which is w bar, but x is changing because x here is 0, x here is 1. So basically this group is w bar z, which is really different from this one. So this term here was representing these two ones, or this one in specific. Now we express it in another way. And the second group again is that group here, which is yz. One may say these two functions are different, right? Yeah, they are different, but you know where they are different? Let me show you. So let me call this F2 and let me call this F1. And let's do F1 and F2 here. So this is F1 here. Let's do it in red, F1. And let's do F2 in green. So I will leave this to you to prove, but I will show you the concept. So if F1 and F2 will have ones at the same locations of F. I mean, let's do that with, this guy, for example. So 1, 1. And again here, let's remove this, But guys, this is wrong. This is not optimal. Okay. So 1 again here and 1 again here, then 1 again and 1 again. Just to try it. Try it, put W and XYZ with this value, you will see that F1 and F2 just equal to 1. Okay. And at the locations of zeros, they are also the same. So 0 here, 0 here, 0 here, 0 here. So what is the difference? The difference between F1 and F2 lies in the don't cares. So for F1, we consider the don't care at 0 as 1, and the don't care at 2 as 1. And the don't care at 5, which is this one, we didn't count it, right? We didn't include it in any our terms. So this means we consider it as 0 without saying it, but this is 0. So we consider this as 0, which is M5. In F2, again, the difference between F2 and F is the don't care. So in F2, we consider if this one don't care at 5, we consider it 1. But the don't care at 0 and 2, since we didn't choose them with any combination, implicitly we are considering them zeros. So let's highlight the differences here, in black, for example. So this is the difference, first difference, second difference, third difference. All of them were in the don't cares. So our first implementation for this function f is F1 has no don't cares, right? There is no don't cares in this implementation. So this is the the ideal definition, the perfect definition of f. And this is the practical definition of f. If, since you have don't care in the original f, so the equivalent f, which you call it f1, is exactly like f. It will not affect your system if you implement your system with f1, but we just manipulate a little bit the value, the don't care value, so that we get better or more optimized implementation. Same for f2. It is exactly the same as f, because the ones here are the same as the ones here, okay? But for the don't cares, we used some of them as ones and some of them are zeros, so also to get an optimized form that we can implement it in a cheap way. Does the cost of F2, is it cheap like F1? Yes, let's do it. So you have here an AND gate with W bar Z, I'm sorry, Z, not Z bar. Another AND gate with YZ, then OR gate. This is equivalent to this. Not equivalent in the same input sense, it's the same output, of course. This is F1, this is F2. I mean, F1 and F2 are legitimate representation of F. Okay? They are both equivalent to F. Although we have different inputs, but we have two AND gates. We have here two AND gates, one OR gate, and each AND gate has two inputs, not three inputs like this one. Okay? So that's basically, guys, how you deal with don't cares in a Karnaugh map, and they are really, a chance for you, an opportunity for the designer to optimize more his design or her design. Okay, so it's an advantage. It's not something bad that you have don't cares. No, you should exploit this in your advantage. Okay, guys, thank you very much. This was all the points that I wanted to cover for K-map this week. We have still one point. This will be a key for our second method for optimization of Boolean function, which is the tabulation method. So see you next week. Bye-bye.